It's a Monday morning. Looks like everybody's fresh. Charlene, have a great weekend. Go out changing colors, so study hard. I think next week is the weekend that tampung, the changing color, is the absolute best I heard. Is it? Isn't it? Yeah, that's what I heard. So I'm looking forward. I hope no rain next week. Okay, Jungan pointed out to me about the assignment I gave you. Just 1 second. There is some error. Take a look at page 7-17, the homework number 4, the reestablished table 3.2 and figure 3.5, based on corrected above equations. Equations I discovered when I prepared, the equation wasn't right. So after I corrected, I asked Higyu to double check. Then he came back to me saying, no, you are wrong. Then he gave another set. Then I looked through again and said, okay, this looks good. And Jungan came in this morning and saying that the equations I put that in is not correct. So I wanted to always check back, and if you have a question, see me, would you? So don't say, oh, Professor Shin, who cares? Then it's a problem. Okay. So that equation, what I wrote was N1 is equal to what's R here? What's R there? Hyun, what's R? If you don't answer, I'll point out. I remember all your name now. Chuil, yeah. 성태, right. 일용. What's R here? R is reliability, but would rather say required, the reliability, required, which is not assigned random variable, specific random variable, or some people call the design reliability, same as required reliability. That's what we know. And this is what is in my note. Gamma function. This is the equation set I give you. This is not what Higyu gave me, but I recorrected, but that was wrong. So what Jungan, he recalculates, so would you please check? Jungan, correct? Yeah. So just to check back, when you put the power, then it's a little bit confusing. And also one additional, this is the book is also wrong. But you know, Isaac, this is really first edition, so I'm going to send the email to Isaac, tell him this is what my students discovered and all. So we have to really help him up to correct. And also, if you look at the page 7, this is a page 717. And the page 716, there is a variance equation. Variance equation. And see that equation. Jungan this morning reported to me this has to be the square there, which means the whole thing square. Okay? Square has to be there, but please check, would you? Variance has to be cm square. If you don't come back to recorrect, I'll accept, and I'll check back, of course. Okay. Higyu, would you check back once again? Okay, the cases we looked through last week was actual stress. Actual stress is random, and strength or yield stress is R, deterministic. So that's what we studied with a few different models. And this week is rather short week. Today, Monday and Wednesday, and I announced it Friday. We don't have a class because we are going, myself and our lab students are going down to Mexico in Busan. So this Friday, no classes. But Friday next week, on the scheduled time, we have a class. Then in addition, at 1 o'clock, we have a 2-hour midterm exam. It's very comprehensive, even if it's an open book, okay? And so I don't want to give you any makeup class that suffices and all that. Okay, this week we're gonna do four. We're gonna do for what? So we have cases, and sigma s, sigma y is what we usually deal with, and we are going to do some cases. The yield stress is the random. That's what we have to do, right? Right, Julie? And we're gonna have this guy is loading over the actual stress or actual loading is deterministic. And in this case, I'm going to do, there are a few different cases is what we're gonna do. But in addition, I'll just let you do one more case, which is slightly confusing. Among the model, which model do you think you might have to pay attention? Normal, log normal, Weibull, exponential, and Rayleigh? I feel log normal is a little bit trickier because log normal, the natural log of x follows what model? Probability, the normal distribution model, if x follows the log normal. That's a little bit more thinking. So what I'm gonna do here, first I'm going to, this doesn't change, it's deterministic. So model, easiest model to understand the philosophy is a uniform probability model that we're gonna do. And the second, we're gonna do exponential. Probability model. And 3 has more engineering cases, Rayleigh probability model. You know, Rayleigh is a pretty well-known scholar historically. All that acoustics area, he wrote the books and all that. So all the days, one scholar covers many different fields. And 4, normal distribution. 5, log normal distribution. I'm going to cover 4. Then you do the last one, would you? Yes. You do that. You don't have to turn in, because I'm going to put that in the as a part of the exam problem. Then you can really say, oh, this is, I have done before. So this is log normal, you do. Because some of you screwed up. When you do the homework for the case, previous case, actual stress is log normal, and this yield stress is deterministic. So a little bit trickier, but not that really tricky. That's what we're gonna do, okay? And as you look at approach is really almost identical to the cases we studied last week, but definition of reliability, which is the probability such that actual stress is less than the yield stress. In that definition, which part you must treat as a random, that's the differences, okay? And then of course for the random, in this case is yield stresses, so we have to get the cumulative probability distribution function to get the reliability expression. That's about all. For the next week's the generalized, the case is random to random. Then from now on, from after that, it's going to be all random to random. Then we're going to get into the really failure surface concept. And toward the end of next week, I'm going to give you the two files, which is rather a thick file, at least 50, 60 page, but you can print it here, right? And black and white, some page you can print a color. Professor Du's the couple chapter, that's what we're going to do. And here we're going to do the first case. The first case is sigma s and sigma y, and this we're going to assume uniform distribution. Deterministic. This is deterministic. So for the uniform distribution, so as we did sigma y, and this is f sigma y, and this is the similar case shown last week. The sigma y, this is lower bound, this is upper bound. Uniform distribution. And here, the value here is what? 1 over sigma y u minus sigma y L. Then when you multiply, area has to be 1. So that's the probability model. Before, the sigma s was a probability model, and for the probability distribution function, it's going to be like this. This value is equal to 1. This is, of course, the 0. So here, the equation of this straight line between lower bound and upper bound is, of course, sigma y u minus sigma y L, sigma y minus sigma y and L. When sigma y is equal to 0, what happened? Let's see. When sigma y is lower bound here, same thing minus same thing is 0. When this guy is upper bound here, it cancels up and down, then this is a 1. That's what the result would be. So this is summation of the density functions, right? So now you're all set to solve the problem. So, but just to write, let's write this one. So we are dealing here. Our target is to get the reliability or the probability of the survivor or probability of the failure, which is complement each other. So of course, density function, you can get it from here, which is 1 over sigma y u minus sigma y L. That's clear. We need this. Why we need this? That's a probability model. Sigma s is has no probability model. Then you have to associate this information to the reliability or probability of survivor, things like that. So to do that, this is a probability. Yunso, what's the expression in the parentheses? Look at me. Huh? 50 chance to win. So it's open book. That's why. What's this? Huh? I'll wait. And the two parameters you have to work with, right? For the probability of the failure or probability of the survivor. SOR. Actual, Isaac used actual stress. Doesn't have to be actual stress. It can be like a loading. Some books use a P and R. I just mixed in the previous note. If you look at the loading, the R, the strengths. So S is deterministic, right? Right there, deterministic. And this is gonna be sigma R. So now for the reliability, strength has to be higher than sigma S. For the reliability, I am going to delete the equal sign. As Kiwan mentioned, that's, I think, very consistent. When you deal with the probability of failure surface, then that include that failure surface as a part of the failure region. Then for the safe region, you don't have to put equal sign, right? So depend on where you put that in. So this is oh, this is what do I define here? What do I define here? Hey, Monday morning, 10 o'clock. Is this correct expression? Say no. But this expression is what? This expression. That's a reliability. I mixed two different things in my thought. Because I pay really attention to Yun-Suk, that's why I screwed up. I'm not accusing you, Yun-Suk. I love you. So what do you have to do? This is what? This is a cumulative probability distribution function for the yield stress or strength, right? So to do that, sorry, but excuse is Monday morning, but that's not true. That's not right. So sigma y is less than equal to sigma y. That's correct. Cumulative probability distribution function, of course, which is nothing but the summation from mathematically minus infinity to sigma y f sigma s x dx. This is really what notation you use doesn't matter. That's really integration parameter, right? Then this is equal to, start from here, up to this region is 0. From here to here is that equation. Beyond the upper limit is going to be simply the 1. 0 and 1. Between is sigma y, this equation, minus a sigma L, sigma y upper, minus sigma y lower. This region is between sigma y L, sigma y, sigma y u, and this is sigma y, oops, I'm sorry. This guy is 0 is below. Sigma y is less than sigma y L. We have to put equal someplace. This one is sigma y is larger than. Just identify this red color, the region. And now you have a probability model, which is nothing but the uniform or rectangular probability, the model. And now you can, the whole job is to express R, which is equal to probability of survivor. Sometimes you use that, or PS is really same thing, and no differences. And this is equal to the one which I erase is a probability such that sigma S is less than, not equal to sigma y. You can use these expressions here from there. Then what we're gonna do is probability, which is the reliability is 1 minus probability of failure. Surely Monday morning. I had a great sleep. PF. Probability of the failure, right? Simple. Then probability of the failure is 1 minus probability that sigma y is less than equal to sigma S. Strength is less than. The way you can think is, okay, failure. Strength is less than the load. Strength is less than the actual. So over here, we have right there, so this is equal to 1 minus F sigma yield for sigma S. So simply this is R is 1 minus F sigma Y. 1 minus of this guy, 1 minus 0 is 1. 1 minus this guy is the second region. 1 minus 1 is equal to 0. So 1 something 0 for the reliability, right? If you just put that in here, then here 1 minus 0, 1 minus 0 is 1. Second is 1 minus sigma S minus sigma YL, sigma YU minus sigma YL, and 0 as a sigma. Oops, I'm sorry. Question? Q1. Question?
Yes, I understand because
yeah.
the last one of the PRE, for the reliability comes using the sigma S in there, but for the cumulative, the probability model, we're using the sigma Y.
I don't find. Okay, let me. You have a question. Let's resolve. It's the best to do in the class. This you have problem? Next. Okay, 1 minus, this is a probability of the failure. So 1 minus, this is yield is less than the actual, correct? So it's 1 minus here. So then now this is y, this is that. Probability yield is less than this guy. This happens. Sigma y, you have to change it to whatever is in here, which is a sigma s. You see, you had, this is deterministic, right? Nothing to confuse. That portion is a little bit confusing. But that's a specific value of sigma y there. You can put, this is the yield stress model. So this means here is a probability random variable sigma y is less than equal to the specific value of sigma y, right? So then sigma, if you put this guy as sigma s, you have to put the sigma s in the yield stress model. Yeah, I'm glad you asked a question. I was going to point out. Question was immediately, why this is sigma s rather than sigma y? Yeah. Kyung-suk, clear? Say clear. Nothing to, don't confuse. It's, easily. Okay, so now all I did was this model is identical to this model, but in this case also sigma y I have to replace to the sigma s. In the process, this is reliability model. This is simply yield stress model. Got it? Nothing to confuse. So here, this identical YL, this is sigma YL, sigma Y, sigma YU, and sigma Y is greater than sigma Y. Up to here, question? Smile. This is, what I did was this, in this model, all I'm going back out here. To get this, I have to put this guy, sigma y. This is simply, think of this, this is deterministic value, specific value. Model is yield. You're comparing in the model what happened if yield stress, the actual stress approached the yield stress. That's what we are comparing there. To define the probability of the failure here. This is a probability of the failure. You have to compare this guy to that guy. If yield stress is less than the actual stress, failure occurs. Then you are dealing what probability? What's the chance? Okay? Hey, open your heart. Then accept it. Yes, so easy? Very easy. Joel? No problem? Hey, come on, yes, no problem. That's the answer. Yonghyun? No problem. How was the baby over the weekend? Good? Good, right? Yeah, that's good. Okay. So, any additional question? Arlene? Problem? So, a couple of parameters for the uniform distribution function. Couple of parameters is we have done it before the last week. So e to the y. What's the e to the sigma s? What's the e to the sigma s? What's the expected value of sigma s? Louder. Sigma s. Why? This is a deterministic. So this is sigma s. Naturally, say that's a stupid question. Stupid question. This is a constant. This is 1. No distribution, simply addition is 1. I'm sorry, but I would rather say, if this is x, this is dx, sigma s is a constant, put it out, so which is sigma s, summation of fs dx, this is equal to 1 back to sigma s. So this is 1. But this guy, you have to actually do the calculation first moment. So limit is sigma y L, sigma y u. Below is 0. Above is the result is 0. So sigma f, sigma y, sigma d sigma. You know this guy. That guy is nothing but this guy. So, which is equal to sigma times over here is 1 over sigma y u minus sigma y L. And the sigma, you have to the sigma y L, sigma y. Even if such a simple model, I would have put that 1 in the exam, because it's good to remove any possible confusion. Then if you do that, then you have half of plus sigma. This is u. Graphically speaking, you're looking into this guy. You're looking at that guy from here to here. What's the average? Average mean is half, which is half of this guy plus that guy for the uniform distribution. That's it. And then you can compute the variance of sigma y. The variance is the standard deviation square in terms of the integration. It's a second moment, it's a variance. So which is sigma y minus mean. Mean, sometimes I use this guy, right? Same thing. This is a dispersion about the mean. And F sigma S sigma y d sigma y. This is nothing to confuse here. This is yield strength. That's why I put that in here. I put that in here. I put that in here, which is integration parameter simply. So I can use this, no problem at all. Who cares about the notation of integration parameter, right? So if you do that, the calculation, so this is second moment, okay? So 112 sigma y u minus sigma y l cube, I'm sorry, square, because this is second moment. Using these two equations, reliability model can be expressed. It's all in the book, in the lecture note. So you can express this guy from this guy, and sigma y u and sigma y re-express as a function of mean of sigma y, mean of sigma y, and the variance or standard deviation of sigma y. To avoid any confusion, I didn't use the simple notation we usually used before to express this as standard deviation of sigma y is confusing. So rather than using this notation, and that's what the Lishkov also used, and the square root of the variance of sigma y, then it's very clear this is a standard deviation of the yield stress. Standard deviation. Then express this as a function of the mu sigma s, and also square root of variance of yield stress. Then you can simplify and all that. That simplifies and express the reliability as a function of the mean yield stress and the variance or standard deviation of the yield stress. That's what the vendor's spec, they have to show in the spec how good our product is. Okay, so if you look at this, this is a mu sigma s, sigma y plus square root of 3 variance y minus sigma s 2 3 variance of sigma y. Or you can express by introducing the N1. What's the N1? Central safety factor, which is ratio of the mean of yield over the mean of the required stress that happen to be constant in this case. So if you do that, then N1, 1 plus 3. This is nu sigma y minus 1, 2. It's a closed form solution. That's the beauty. That's the beauty. That's the beauty. This is a nu. So over here, this guy is equal. Oops. I'm sorry. I better be really careful. I better be really careful here. So every time I better be really defined. N1 is ratio of the mean of the yield over mean of the actual stress. This nu is what? Coefficient of variation of sigma y, which is equal to the squared this is a standard deviation. We use a notation to eliminate any confusion over the mean of sigma y. Remember, if this guy, as we saw the case on last Friday, if this is higher than 0.5, 50%, that spread is terrible. Then you better abandon to conduct any probabilistic analysis, because you better buy the new product from the vendors. Otherwise, you are wasting money. If you use that material to build a ship, what do you call it? FSPO? FPS, so terrible. Better not doing it. So this is a good measure, coefficient of variation. This is for strength. This guy is nearly 1. Nearly 1, abandon the ship. Not gonna work. If this is no good, don't do it. So this is an expression for R, and then always at the end, not always, N1, central safety factor, which is 1 plus the square root of 3. This is nu sigma y, coefficient of variation, 1 minus 2r. R is design reliability or required reliability. Design reliability. Good name, design. Oh, I want to have reliability of this system as a 0.99999. Then this goes 0.999. If coefficient of variation is large, 50% and even higher, this N1 central safety factor has to be very high, stupidly high. You can't design that. Okay, I'll stop here, then we'll continue to finish up this family of a problem this Wednesday. Then you have a chance to the review from the lectures up to the Wednesday. Then we'll continue week after this week. Okay, I'll stop right here.